Hi everyone. Today's course would be about the actions acting on the structures. So we're going to start with the wind loads, since that the wind load is so important that it cannot be neglected for a way or another. So before we start, we need to figure out that we are using the Italian code. The Italian code is called the Norme Tecniche per la Costruzione, which is the technical standards for the constructions. And it's following the European code, which is EUROCODE, the part of, okay, so this is EUROCODE part 1.4, since part 1 representing the actions on the structures and point 4 refers to the wind load. Okay, let's just go straight away on the topic. What is the wind load? Before we start, it's nice to understand this. If this in 3D building, this building got acted by wind. As a designer engineers, we would like to understand two things during or regarding to this wind. First one would be the velocity of this wind, the speed of this wind, and the pressure of this wind while it's acting on our designed building. So starting with the velocity, because we can't estimate the pressure before we calculate the velocity first. The first factor we will have here is the reference velocity VB. And VB is the velocity of the wind, or the wind speed. By another meaning, that acts at 10 meter high of the building, including this is the building, at 10 meter high. This VB is acting at 10 minutes of loading on the building for assumed returned period, which is TR, and we're gonna speak about the TR later on, for 50 years. Or you can say 50 years of the construction phase and the usage phase of the building. So the first equation for the VB is given by VB is equal to VB naught times CP, or we can call it CA. First of all, you need to understand these coefficients, such as CA, are coefficients able to be changed as a name from a code to another code. So don't make this concept for your mind. This is just a mentality of the engineering. So if you understand that we have the reference velocity is equal to some coefficients, if the name is changed, this is not a big deal for us as engineers. If you're working today in Italy and you move tomorrow in another country, this shouldn't be a limitation for you. But anyway, let's start. This CA is nothing but CA could be equal to 1, or CA could be equal to 1 plus KS times AS over A naught minus 1. What is all of these? So let me tell you, the KS and the A naught and the VB naught are coefficients or values given by the country code. So by the Italian code, which is following the European code, as we said, but it cannot be following the European code 100%, because each country in the European Union has its own situation and has its own wind speed, you can say geographic location and situations and so on. So you can't take it as a common factor, the European Union code. But anyway, we just applying now the Italian code. So regarding to the Italian code, as you're gonna see in the figures in front of you now, so by knowing that first of all, the Italian country are subdivided into 9 zones, as you see in the picture in front of you. These 9 zones, if you know which city you are constructing the building in, let's say you are constructing in Milan, in Rome, in Venice, in wherever, the place or the cities that you are designing the construction to be built in, you have to follow these 9 zones. It would be 100% one of these 9 zones, because it's set by the Italian government. So if we know the zone, you can see in the picture in front of you or in the table in front of you that you can get VB naught and you can get A naught and you can get KS. So now we have this known, and this known. There's one more left unknown to sort out this equation. Yes, that's it. The AS is unknown. So now we don't know what is the AS and how to get it. AS is nothing but the altitude from the sea level. And it's given by meter. So what is this? Just to understand, if this is the water or the sea level, and this is the level of the city or of your building, this value in here called A naught, okay? And if the ground, of course, looks like this, if you are in here and the building your construction in here, this called AS. A naught is in meter, AS is in meter, so both of them remove one another in this equation. So this is by meter, this is by meter, so it became a unit less. And now you can calculate the CA. Anyway, you need to understand that this CA, this is CA, cannot be less than 1. So it's equal to 1 or even more. Now we calculated the CB, right? Which is the reference velocity. What else do we need to do for our design? For our design, we need a step number 2, which is calculating something called the design reference velocity. And this V is called VR. And VR is nothing but VB times CR, since this is R and this is R. VB is known now, right? Okay, what about the CR? CR is a coefficient that depends on the TR that we mentioned before, the returned period. And this TR normally assumed to be 50 years. Just in case that this TR is equal to 1 year, or this TR is equal to less than 1 to 5, or 5 to 50, or TR is even more than 50. In the figure in front of you, or in the table in front of you, in this shape, you can see different equations of how to estimate or to calculate CR with respect to TR. What we can say is that if we have a figure in here, this is TR represented in years, and this is CR, the coefficient. We have a shape like this, upward relationship. So in TR equal to 50, like this, the CR is normally equal to 1. In TR equal to 1, the CR is equal to 75. By the way, you can calculate straight away from the relations in front of you in the page how to calculate the CR. Now we estimate and we calculate the design velocity, right? So we got the first unknown or the first requirement to calculate the velocity or the wind load acting on the building. Now let's go to the step number 2. For step number 2, it's called the pressure, right? I guess you guessed this. We have two types of pressures. Why? Let's draw this real quick. Okay, so this is our building. You can just, let's assume it this way. Sorry for the horrible drawings, but I guess it's fine. At least you understand the idea. So for here, assuming that the wind is coming from this side, so acting in this side, what's going to happen to this building regarding to the wind load? I'm going to tell you. Here we will have some loads like this acting perpendicularly on the column side. What happening here? Yeah, we will have wind loads perpendicular on the slope we have, or the roof we have. This roof might be flat roof, no slope, could be one slab roof, could be two slab roofs. We're gonna see all the situations and all the conditions. But at the moment, this is a perpendicular pressure on the construction or on the building. We call this as B. And this B will be equal to QR or QB times 3 coefficients. I know this is a lot of coefficients, but we're gonna calculate all of them. Designing is not something easy, and it's important, and you need to take a lot of coefficients and factor of safeties. So anyway, just try to be economic enough and safe enough. This is the engineering, and this is how we design. So we have CE, and we have CB, and we have CD. What is this 4 factors in here? The QB is the kinetic pressure. the CE is a coefficient called exposure coefficient. The CB is called the shape coefficient, and the CD called the dynamic coefficient. Okay, now we are familiar with the four coefficients. There is another type of the pressure we haven't mentioned yet. Yeah, let me show you why there is second type of the pressure. In here, if the wind is acting from this side, so what happens to this side? And by your imagination, because you are an engineer, in this side, the other side, or the other lateral side of the building, what's happening here? Yeah, what's happening is that the wind is coming from this side, acting. Let's have an elevation, okay? Assuming this is the elevation and the wind coming from this side, there is a friction happen this way between this side and the wind. This called the coefficient of the friction. So from here we have another pressure that is equal to QB, and the QB is nothing but the kinetic pressure again, times the CE, because the CE is the exposure coefficient, and the exposure coefficient doesn't change or doesn't depend on the shape. It just depends on a lot of elements or a lot of factors we're gonna mention later. And CF. CF is the friction coefficient. So now you should be familiar with the two pressures that the wind acting on the buildings. That's an overall. Let's start calculating all these factors. So first one we have it here is the QB. I'm just gonna change this. Okay. The QB. What is QB? Is the kinetic pressure. We have this equation here called rho times V power 2 over 2. The rho is the air density. And most of the time, it's 1.25 kilograms over meter power cube, or cubic meter. Okay. What is V? This is the question here. Shall we take it VR or shall we take it VD? If you know the designed year of the building and it's exceed the 50 years, you need to consider the VR in your equations. Because, again, going back real quick to the equation of VR, it's VB times the CR. CR could be less than 1 or bigger than 1. What's gonna happen if it's in less than 1? The VR will be less than VB, right? Now, staying safe and take VR is equal to VB at this situation. But in case the CR, which depends on the TR, in case that the TR is bigger than or equal to 50, in this case, no, you need to take VR in your calculations because it will be bigger than a VB. So this is so important to know which V we're gonna use. At the moment, I'm just gonna keep it VR, okay? Assuming that the building or normal buildings last or have a lifespan of 50 years or even more, from 50 to 100. So now we calculate the kinetic pressure. Let's go to the other important coefficient, CE. The CE have 3 steps, the exposure coefficient. Have 3 steps. First step, as you will see in the picture in front of you, is called defining the class of soil registry. And this, by the Italian code, are given into 4 classes, like this. Will be also appear in front of you in front of the screen. So we have 4 classes, A, B, C, D. A, as you can see, that it's urban area of 15% of the total surface is used for the buildings. What does it mean, 15%? I will just be real quick in this because I know you might be designing by another code. But anyway, if you read the note written in here, you will find that they consider, if this is the building, is kept 1 kilometer of each side, this create an area here, right? This area should not be less than 15% of buildings surrounding this area. Okay? What if it's less than 15%? We have the category number B, or category B, okay. Anyway, it's not number. So here is the urban area that is not category A, or industrial area, or whatever. You can see in the screen, it's written clearly. And then we have category C and category D. Once we know the class of the soil registry, we go to step number 2 of calculating the CE. So it will be in here. The second step. Second step will be going in the tables or the figures. These figures in front of you depends on 3 main factors. Here you can find the soil class, okay? And here, this is the zone. If you know the zone, and if you know the class registry of the soil, and you know the horizontal distance from the sea level, I'm sorry that it's written in Italian. I tried to bring all the data in English, but it was quite hard since that we live in Italy, so everything is written in Italian. But I'm giving you what is written. This is the sea, and here this is the coast, like in here, and then you go upward to mountains with a specific height. You see what is written here is called the categories. These categories that we can see in here, we go for the third step. If you know the category, you will get some coefficients such as KR, Z naught, and Z minimum. Okay, by the equations given in front of you in the picture, you will see we have some unknowns such as CT, KR, Z naught, Z minimum, and the normal Z. What are these? The CT is the topographical coefficient. We will speak about how we can calculate it in the next page. The KR, the Z naught, the Z minimum are given by the table. After we define the category, let's say our category is in Italian, in the Italian code, is divided into I, double I, which is 2, until 5, okay? So let's assume that we are in category number 2. You can go straight away to the table for the category number 2 and get these values, but you'll still need to understand what is this. The KR is the soil coefficient, the Z naught is the roughness length, and it's given by meter. The Z minimum, what is the Z minimum? Okay, these 2 points are very important, and a lot of people or a lot of engineers fall in this point. This is the ground level, and this is the buildings that we have. Let's say this building is subdivided into like 4 or 5 floors. This in here, this distance, this height in here, called Z. You can call it Z1, okay? Or yeah, you can call it Z1. This one is Z2, Z3, and the same point until you reach the end. At the end, this Z will be equal to H of the building, the height of the building. Okay, so this Z, we have 2 situations or 2 calculations for the CE, as you can see. One of them, if this Z is less than Z minimum, and if this Z is bigger than Z minimum. In the case that it's less than or equal to Z minimum, what is the Z minimum here? We didn't say it yet. The Z minimum is the minimum height for the floor allowed at this category. So this is Z minimum. Sometimes, let's assume a quick example here, that this Z is equal to 3.3 meters, okay? And the Z minimum is equal to 8 or 5. Let's just say it's 5. What's gonna happen here? For the first floor, the CE, by the calculations or by the equations given to you, you can get the CE is equal to this equation. Just replace the Z value by the Z minimum value. What happens if the Z exceeds the Z minimum? You take the Z with the actual value as it is, which is the height of 3.3, for example. 3.34 times 2, so we are in the second floor in this part in here. So this is going to be 6.6, right? This is higher than 5, so we take this value in here. I hope it's clear for you, this calculations for the exposure coefficient. Now we calculated, okay, I will just write in here. Okay, I will just write in here the equation real quick. So we have the pressure equal to QB times the three coefficients, right? CE, CB, CD. The QB is already calculated, or we defined it. CE, we just got it. Let's go for the third coefficient, which is the shape coefficient. Before we start the shape coefficient, let's draw this again. And let's see what is happening here. Okay, so by considering that this is the 3D and this is the wind direction, what this wind do to the building again? Yes, it's acting perpendicularly on this side and perpendicularly on this side too. What happens to this side and behind? What happened to the other side behind, estimating or considering this as the symmetric line? You need first to understand this area in here, or this surfaces in here, this one and this one, are called the upwind surface. Okay? And this one behind, this side behind, or this surface behind, is called the downwind surface. This side here is called the lateral surface. Okay, so we have the three coefficients, or we have the three surfaces here. What's gonna happen? The CB acting on here by compression to these two sides, and for this other two sides, we have tension happens in here. Why? Because the building in the 2D model, if the wind acting this way, this building won't to be like this. Okay, this is gonna happen to the building. So this side will have a compression, this side will have tension, this side will have compression, this side will have tension. Okay, so this is what's happening when the wind acting from one side. Normally the wind doesn't act or doesn't come from one side, but we consider it as the maximum wind acting on the building from a specific side. We call this as a main wind direction. Okay, so what else we need to estimate in here? Okay, for this side, the outsides, this one in here, this one in here, this one on the other side, this one in the other side. This called the CB, which is the shape coefficient. We add E, so it's the external shape coefficient. For the internal sides or surfaces for the building, we call it CBI. This CB depends on two things. So for factor number 4, I guess, or number 3, we have the CBE, which is the external. You can see by the picture in front of you that this CBE by a chart like this when, I'm sorry for the Italian charts, but the sopravvento means the upwind surface, the sottovento means the downward or the downwind surface, and here we have the lateral surface. Okay, if you know H over D, what is H, what is D? Sorry for forgetting to say this. So we have the building here, again, must be in 3D, but it's fine. Okay, the wind is acting from here. This will be B, the distance inside will be D, the high will be H. Notice this please. H is called the reference high. This reference high should be the highest point of the building. Because if you see, we also have this one, right? We have this high in here. But this high is not the maximum high. We consider H as a reference high of the building, which is the highest high in the building. So this is important. By knowing H over D, we can, let's say it's in here, we can go upward like this, calculating the lateral and the downwind and the upwind. This is for the CBE external. We have also the CBE external for the roof, right? What's gonna happen for the roof? The roof have a different slopes. Based on the slopes of this roof, we can estimate the CE. What is the slope in here? If we have the building, it looks like this. This is alpha in here. What's gonna happen when the wind acts from this side? What happens is that we have the load acting on here and also in here, right? This will be positive CBE, while this one will be negative CB. The values of this CBE depends on the slope of this alpha. If this alpha is bigger than or equal to 60, or if this alpha is less than is bigger than 20 but less than 60, and if this alpha is from 20 to 0. Here you can find in the figure in front of you the values of this CBE. Not only this, but you can also see in the other figures that the CBE it change based on the slope direction. If the slope looks like this, is not this called Dubitsch roof. We have also this type of roofs, and we have also, just like this is fine. And we have also this type of roof. The direction of this monopitch roof or the Dubitsch roof control the sign of the CBE. So this is more or less for the external shape coefficient. What about the internal shape coefficient and from where it comes? So we have three main cases for the CBI, and the I refers to the internal. We have the first situation, if this building is totally closed, no windows, no openings, the internal CBI, the CB will be 0. In the other case, that the opening is here and the wind acting from here, and in case that the building looks like this, the wind is acting from here but the opening is on the other side, not on this side, what's gonna happen to these? So you need to understand why there is CBI in here. I'm gonna explain to you right now. If the wind is acting from here and this is the open, the wind is going to enter the house or entering the building. This wind inside will push this side to the outside direction, right? This external sides or this external pushes represented by plus sign. What happens for this side? The wind is acting on this closed side, but is also coming from the other side, right? Entering this window to enter the house. What's gonna happen in here? This is, let's say this is the wind effect. It's going to be inside the house or inside the building. So at this case, it will be minus CBI. We have two different values. If this opening area, the opening area, is less than the third of the total area, then CBI is equal to plus or minus 0.2. The 0.2 here would be plus if the opening at the same direction of the wind, would be minus if the opening on the other side of the wind regarding to the wind direction. If this area, the opening area, is bigger than, if the opening area is bigger than the third of total area, then the CBI will be plus 0.8 or minus 0.5. And again, I guess you now so familiar why it's a plus and why it's minus, right? It's a plus again because of this situation, and it's minus because of this situation. So now we calculated the internal and the external. There's a few situations or few cases here that is special case, which is if you have the building with multiple roofing, okay, just like this. I'm sorry for the shape, we can just change them real quick. So it will be Okay, just let's say like this. And the wind is coming from here. What gonna happen? What gonna happen if the wind coming on building looks like this? As we say, this is called multiple do-pitch roofing, and this is a single. Okay, we don't want it to be single, so we will just do it in this way, like this, multiple mono-pitch roof, and still the wind is acting from this way. The wind directions or actions will be this way. Here will be this way. What do you think in here? Yeah, it will be tension, this compression again, this tension again, this compression, and this tension. Okay? So the signs here would be positive, positive, this one would be negative, positive, negative, positive, negative. What's gonna happen in here? Same to what happened to the monopitch roof. Wind is acting this way and this way. And this is what's gonna happen. But there's the code say something is so interesting and important. That take care, because after the first span, if this is CBE, because we are speaking about CBE in here, this CBE will be reduced for the second span by 0.8 CBE, and here will be 0.6 CBE. Again, you don't need to save the numbers. The reduction is by 0.25 of the CBE, of the external CBE acting on the element. Again and again, you don't need to worry about this at all. This are given by your country code. Could be familiar to the Italian one, could be the same even value. The names, I would say, the names could be the same, because I just forgot to mention this. The CE, which is the exposure coefficient, are locally, because you can't consider the zones that in Italy, which is 9 zones, as the same in your country. Your country might have more or less zones with more or less situations. The values would be familiar, but the zones cannot be. While the shape factor is a global factor. We have something called a local. We have something called the local shape factor, which is CBE 1 or CBE 10. Don't you worry about this, because now we are talking globally about this situation. So this is how you can calculate the CB. So after calculating the internal and the external, you need to understand that CB is equal to CBE plus the CBI, okay? The external plus the internal. You take them and with respect to the signs. So for example, if you have, you can see in the figure in front of you that we have a different situation where the wind is acting from this side, the wind is acting from this side in here, and these values are positive 0.8, and this is 0.03 alpha minus 1, and so on, and this is minus 0.6, I guess, and this one also. So you see that the CBI might be one time positive, you can say positive 0.2, and sometimes is negative 0.2. What is going to happen to the CBI on this side? Yes, the CBI on this side, or the CBE at this side, will be equal to 0.8, which is the CBE, minus, in this case, minus 0.2, and it will be plus 0.6 at the end. This is the CB. Because again, I don't know why it's gone, but sorry. Again, the CB that you are using here is the summation with respect of the sign. Then we come to the last coefficient of this video, then we all done. This was a theoretical lecture. At the end, and in the next video, we will have example and exercise of how to estimate the wind load on a case of a study of a building, define the zone and everything. But you need to be familiar with this design, otherwise you will not understand anything in the exercise. So the CD is the dynamic coefficient, right? This dynamic coefficient in most of the study are equal to 1 or assumed to be 1 if the height of the building does not exceed 80 meters of height. What's gonna happen in case that we have a steel structure, and we have two other cases. One of them, as you see in the picture, is a composite between the steel and the reinforced concrete, and the last one would be if it's a pure reinforced concrete building. You can just go by knowing, again, we have this, okay, like this in 3D again, yeah. If we assume this is H, and this is B, and this is D. If you know H and you know B by the meters, you can intersect on the figures you have in front of you in the picture, like in this and this, and you get a point. This point can represent for you the CT, the actual dynamic coefficient. Okay, that was it for today. I would like to thank you for your patience, for listening. And if you have any questions, and if you have any doubts, or if you want any references, if you need help even in EUROCODE and I can offer you help, please don't hesitate, and see you the next time.